session of the Applied Networking Research Workshop 2020. Unfortunately, the link in the IETF data tracker for this session was wrong, so we may give folks 1 or 2 minutes extra to join. It looks like people are joining now. In case you get questions from coworkers or friends who want to join, the link in the data tracker has been fixed. The correct link to this session is also up on the ANRW website. Okay, good afternoon, everyone. I'm going to start with the introduction slides from the chairs. So we have a few more minutes for people to join. Welcome back to the Applied Networking Research Workshop 2020. My name is Ron Tressek-Dij and my co-chair is Mirja Kulewind, who's waving to you from on the screen. A quick, hold on, there we go. A quick reminder that we are generally supported by Akamai and Comcast. And a quick reminder of logistics and links. There is a Slack channel on the SICOM workspace specifically for this workshop. If you would like to have a second screen to chat on, or if you want to ask questions to our speakers later on, you can go to the SICOM Slack workspace. There is a joining link shown here on the slide, but it's also up on the ANRW webpage. The program and all of the PDFs of the papers are available through the IETF website as well. This is also a reminder that this session is being recorded and will be made available on YouTube after the workshop. So if you do ask questions and if you do decide to share your video, know that this will be recorded and shown on YouTube later on. And all of the slides are up in the IETF data tracker. A quick note for those of you who were not in the previous session and have not been participating in the IETF so far, if you would like to join the queue for the question and answer session, please click on the little microphone logo with the hand next to it to join the queue. And you can also click on this if you decide that your question has already been answered and you would like to leave the queue. This session has 2 papers in it, and without further ado, we're going to go to our first speaker, and our first speaker is Stephen McQuiston, who is a research associate at the University of Glasgow. He works on projects looking to improve the Internet Protocol standardization process and its outputs by designing tools and interventions that address both technical and social challenges. Alessandro, if you could start the video, please.
Hi, I'm Stephen McQuiston from the University of Glasgow.
Sorry, just 1 sec. I was sending the video to the wrong room.
Hi, I'm Stephen McQuiston from the University of Glasgow. In this presentation, I'm going to outline our paper, Parsing Protocol Standards to Parse Standard Protocols. Thinking about how Internet standards documents are typically written, they're generally centered around descriptions in English prose. To some extent, this is desirable. Natural language makes it easier to exchange ideas, to facilitate discussion, and to build consensus. And these are all important parts of the standardization process. However, as protocols become more complex, the limitations of this approach become clear. Natural language allows inconsistencies and ambiguities to be introduced into documents. This makes it not only more difficult to express a concise, consistent specification, but it in turn makes it more difficult to develop an implementation that conforms to the standard. There are a number of more formal, structured languages that would not only make documents more concise and consistent, but that would enable machine parsing. In particular, we want to think about protocol description languages that describe the syntax of protocols and how they should be parsed and serialized. And there are many of these languages, and each is suited to describing different types of protocol. Importantly, using these languages would allow us to take a standards document and use a tool to extract a protocol description from it. This machine readability would also enable automatic code generation. This would let us take a standards document and automatically generate an implementation for the protocol that it specifies. And this leads to a number of benefits, including enabling a test-driven development style approach to protocol design and promoting the use of modern, type-safe systems languages. And more broadly, this architecture of taking a standards document, parsing it using a tool, and producing implementations directly from it should improve the security and trustworthiness of the protocol standards documents themselves. However, there are a number of important factors to consider if this architecture is to be successful. We must consider how the adoption of formal and structured protocol description techniques can be encouraged, and how the architecture itself can support automatic code generation from these different techniques. Now, if we begin to think about what the architecture looks like, at its most basic level, we could write code that takes a specification document, extracts a protocol description, and generates code in a target language. However, documents might contain protocol descriptions in a variety of formats, and we might want to generate implementations in a wide number of different programming languages. By coupling the input description language with the output programming language, code needs to be written to support each combination of the two. Not only is this a significant amount of duplicated effort, but it is likely to make it more difficult to adopt new description techniques or to target different output programming languages. Instead, we want to decouple the input description language from the output programming language using a common protocol representation. In this architecture, standards documents are parsed and a common protocol representation is derived. From this common representation, parser implementations can then be generated. This means that new description techniques can benefit from already written parser generators, and parser generators can automatically make use of new description techniques. In addition, tools can be written to inspect the common protocol representation, allowing properties to be checked or validated. In this presentation, I'll briefly talk about all three components of this architecture, outlining how description languages fit within the IETF standardization process, and in particular, how the social barriers to their adoption can be addressed. I'll also talk about what a common protocol representation should look like, and finally, how automatic code generation can be supported. But first, I'm going to focus on the common protocol representation. And to begin, we'll think about what the requirements of a common protocol representation are. And to do that, we'll start by looking at existing protocol description techniques. First of all, there are syntax description languages like ABNF, ASN1, and the TLS 1.3 presentation language. These are meta languages that are used to describe the syntax of protocols. Each language is suited to a particular class of protocol. ABNF, for example, is commonly used to describe text-based protocols, while ASN1, with support for various encodings, is used to specify binary protocols. However, these languages can only be used to describe the syntax of protocols. But if we want to generate parser code, then we must also capture the semantics of protocol data. For this, we can look at protocol type systems, like ETPL, an enhanced version of the TLS presentation language, and Yang, a data modeling language, or others like DataScript and packet types that are more general. With a basic set of types, these languages allow the semantics of the protocol data to be captured, but they also couple the external format, that is, the bits that are sent on the wire, with an internal representation. Now, for simple protocols, where the external format matches the internal representation, this is sufficient. But for more complex protocols, with contextual, multi-stage parsing, the internal representation will differ from the external format and we need to be able to capture that. So finally then, we have more recent protocol representation systems that allow for a description of the external syntax and a separate internal representation to be captured. While the two systems that we discuss in the paper, Nail and Narcissus, go some way towards meeting our needs, there are important limitations. Nail supports context-based multi-stage parsing, but with weak type guarantees. And Narcissus provides stronger type guarantees, but it lacks support for parsing contexts, which are necessary for complex protocols. We need to provide both strong type guarantees and support for complex protocols. In summary then, what we want is a representation system that builds on these recent approaches, but does so in a way that is both safe and extensible. To that end, we introduce the network packet representation, a typed protocol representation that is decoupled from any particular protocol description language and from any particular output programming language. It provides type constructors for a set of basic type classes that can be composed to model complex protocols. To illustrate the type constructors that the network packet representation provides and the motivation for them, we're going to begin by looking at an example RTP data packet. First of all, at the most basic level, bitstring types are needed to represent raw protocol data. Next, we can see that PDUs can contain sequences of elements of the same type. In this example, the RTP data packet contains a sequence of contributing source identifiers. We need to be able to capture this. We can also see that these basic types need to be able to be composed together into structures with an ordered list of named fields of different types. And often these structures represent PDUs. Within each structure, fields might have constraints. In this example, the V field should equal 2 for an incoming PDU to be successfully parsed as a valid RTP data packet. And more complex constraints also exist. Again, in the example, the presence of the header extension block is dependent on the X field being equal to 1. And again, we need to be able to capture these more complex constraints. Within the header extension block, we can also see the need for contextual data. Here, the first field of the header extension is defined out of band using a separate signaling protocol. However, this value is necessary to determine how this PDU should be parsed, so we must be able to model this contextual data. A protocol itself is comprised of a set of different PDUs or structures, and therefore we need an enumerated type to represent the different PDU variants, and an overall protocol type to represent the protocol itself. And finally, PDUs might have a multi-stage parsing process. For example, in Quick, data arrives as a bit string. These bit strings are parsed into a protected packet structure, and then this protected packet structure is decrypted and parsed into an unprotected packet structure. Each of these transformations is performed by a function. The network packet representation captures the set of typed parameters and the return type of functions. This allows them to be type checked and removes a class of runtime errors. Importantly, these functions can model access to the parsing context, providing a powerful type system for describing complex protocols. In summary then, the network packet representation provides a common protocol representation format that enables state to be maintained between the parsing of different PDUs using contexts, and that also provides support for dependently formatted PDUs, constraints on and between PDU fields, and for multi-stage parsing via typed functions. All of these features are needed to model complex protocols. And importantly, the network packet representation is independent of any particular input protocol description language and from any particular output programming language. And of course, there is much more detail about the network packet representation and its type system, and those details are all in the paper. So, I've described what this middle component, the network packet representation, looks like, and described the types that it supports. So we can now shift our focus to the input protocol descriptions, from which the network packet representation is generated. Importantly, while the network packet representation addresses the technical barriers to the use of formal and structured protocol description techniques in protocol standards documents, there remain a number of social barriers to adoption. To attempt to overcome these, we briefly describe a set of principles that should inform the design of any description techniques that seek wide adoption within the IETF standardization process. Firstly, designers of protocol description techniques should be aware that most readers will be human beings. In introducing new elements or making existing elements machine readable, it should be remembered that they should be easy to understand and discuss. We should avoid introducing elements that cannot be easily understood. Similarly, it should be easy to author machine-readable elements, without special tools or workflows. Authors in the IETF have a diverse array of workflows and tools, and requiring the adoption of a particular tool will likely limit its adoption or exclude authors that don't adopt it. Next, while it would be straightforward to introduce machine-readable elements as an appendix to an existing specification, this should be avoided. There should be a single canonical specification, of which machine-readable elements are a part. Having a separate machine-readable element would effectively introduce a second specification and give rise to ambiguities between the two. We must also consider expressiveness. A given technique shouldn't limit expressiveness. However, given the other principles that I've described, it is important that documents remain easy to read and write. Approaches that are easy to use and address most, but not all use cases, are preferable to approaches that are complex but address all use cases. And while expressiveness shouldn't be limited arbitrarily, it may be desirable to limit it to provide intrinsic safety, security, or computability guarantees for the generated parser code. Protocol description languages should be minimally expressive and restrict protocol designs to those for which safe and secure parsers can be generated. And finally, there are very few elements of standards documents that are mandatory, and it is not possible to force the adoption of a particular technique. As a result, the techniques that are developed need to be flexible and capable of handling those documents that don't adopt the technique. With these principles in mind, we can now think about specific protocol description languages and how they fit within the protocol standardization process and our broader architecture. There are a number of languages already in use across the IETF, including ABNF, ASN1, and Yang. These see small clusters of adoption where a particular group has determined that the technique is well suited to the types of specification they are writing. As a result, any tool that aims to see broad adoption needs to be able to accept multiple description formats, and the network packet representation is designed for this. It is agnostic to any particular input language. Parsing structured languages is well understood, and indeed parsers for ABNF and ASN1, for example, have been around for a long time. And insofar as the network packet representation can represent the same protocols as those formats, it should be straightforward to generate it from descriptions in these languages. However, given the relatively low rate of adoption of these formal description techniques, and the principles from the previous slide, we also want to consider more informal languages, like packet header diagrams, that see wider adoption across the IETF. In the paper, we describe the augmented packet header diagram format. We have attempted to regularize the packet header diagram format while making only the minimal required set of changes to support machine readability. As shown in this example, which is of a quick packet, this format remains extremely close to that in common use, and maintains the packet header diagram itself, which is useful for illustrating the layout of packets. The augmented packet header diagram format also includes a description of each field, using structured text to define constraints and model the use of parsing contexts. In addition, structured text is also used to define functions, and to describe how the protocol is parsed and serialized. In summary, we have attempted to balance the structure and uniformity that is needed for machine parsing, while also maintaining the flexibility that is needed for the format to remain useful in practice. We have developed prototype tooling that supports this format and that generates the network packet representation from descriptions that use the format. Additionally, we have an example specification of the quick protocol that uses the format, and links to both the tooling and the example are in the paper. So, we have seen how standards documents can be adapted through minimal change to use protocol description techniques, and how the network packet representation can be generated from them to provide a common intermediate protocol representation. Next, we'll briefly look at the final component of the architecture, parser generators. The automatic generation of parser code can provide a number of security benefits. Generating parser code automatically from protocol specification reduces the risk that bugs are introduced during manual parser implementation. But there are further benefits that come from generating code from the network packet representation. Having a common intermediate protocol representation means that the core code generation functions can be implemented once, and this should ease the development of new code generators for different languages. Our prototype tooling supports the parser combinator paradigm, where the parsing of a complex type is broken down into parsers for the simpler types that it contains. To demonstrate this, we'll consider again the quick example written in the augmented packet header diagram format. Our prototype generates types and parser combinator functions, starting with those for the types contained in PDU structures, and then those for the structures themselves. For each of these, the constraints in each field can then be expressed in the target language to be checked at runtime. In addition, stubs are generated for functions. While the network packet representation language does not capture the implementation of these functions, it does capture and type check function signatures. In summary, the network packet representation allows support for different parser models, like parser combinators, to be implemented once and reused for languages that share that model. Writing this code once is likely to reduce bugs and promote the development of generators in different languages. This has further implications for security. If modern systems languages, like Rust, can be easily supported, then their use and adoption will be promoted. Importantly, our prototype tooling supports Rust code generation, taking a description in the augmented packet header language, generating the network packet representation, and then producing Rust code as output. Now, we have discussed all three components of the architecture: protocol description techniques that can be easily adopted within the standards process, a common representation format in the network packet representation, and how it can support the automatic generation of parser implementations. Importantly, the network packet representation provides support for complex protocols with contextual multi-stage parsing processes. The network packet representation is agnostic towards any given input or output language. This allows us, with the augmented packet header diagram format, to provide an incremental path to adoption within the standards community. And we believe that this is an initial but important step towards the routine use of tooling that parses standards documents and produces implementations, and that this should ultimately lead to standards that are safer and more trustworthy. Thank you for listening.
Thank you, Stephen. I'll let you in to answer questions from the audience. I saw a lively discussion on in the chat. So if any of the people participating in the chat would like to ask Stephen a question, please join us. And okay, so we have a question from Robin. Robin, go ahead.
Yeah, thank you for the nice presentation. I'm sure you've seen the updates to the quick specs. They're using a new packet definition format now, which was mainly used, I think, to make it more readable for humans. And I wonder what you think of the new format and how, if it makes it easier or more difficult for works like yours to automatically parse.
Okay, so Robin, it looks like Stephen lost his connection. Okay, so he's back. Stephen, did you hear Robin's question?
I did not, sorry.
Oh, okay. Robin, can you repeat yourself very quickly?
Right, so you've probably seen the new packet format and the new quick drafts.
Yes,
quite different. And I was wondering how much do they help or hurt approaches like yours instead of the old one?
So the architecture that we try to describe in the paper is quite flexible about how protocols are described. And so where we outline this packet header diagram format in the paper, that's just an example of how drafts can describe protocols. The real constraint is that these descriptions need to be regular enough that we can parse them out with a bit of code. And beyond that, we really don't mind what format they take. And personally, I think it's great that Quick is using a more regular language to describe these things.
All right, thanks.
We have a question from Lucas. Lucas, go ahead. You have the floor.
Hello, can you hear me?
Yes.
Great, thanks. Yeah, just to add to Robin's point, part of the reason we went for the change in the Quick specs was because of the complexity in all of the variable length fields that happen in Quick packets, and the composition of packets and frames kind of invalidates this very structured, rigid, like well-defined byte boundaries and stuff. So you end up with just like 0 to 32 on the x-axis, which doesn't mean anything. And actually, when we came up with our own kind of scheme, it saved a lot of space in the document as well, which is a consideration. So on the whole, I think it was probably the best direction, and we landed those changes without much resistance, even though we were very far along in the whole Quick document iteration cycle. So sorry, it's not a question, it was just a comment.
Yeah, and I think sort of adding to that, I think it shows that different protocols and different documents require different languages. So for something like Quick, where the byte boundaries really don't make sense to visualize in the document, then something like the representation language that you've got makes more sense. But for other protocols where those byte boundaries are still important, I think the visualizations do help. And so different documents need different languages, and I think the architecture that we've got supports that. So.
Absolutely, and that different visualizations target different audiences. So I'm really thankful for the work. It's great stuff. Thanks.
Thank you. Thanks.
Okay, so we have 2 more people in the queue, and then I'm going to close it. So a quick question from George. Go ahead, George. George?
Hi.
You still, oh, and he's gone. Okay. Oh, there he is. Oh, and he's gone again. George, are you still there?
Might be heard.
Now you can be heard. Yes, go ahead.
So I'm drawn to an observation that it feels you are essentially discussing a collection of heuristics, each of which is a fairly highly structured formalism, but the heuristic is attempt to read diagrams to construct structured code outcomes and strongly typed statements of the protocol. Why aren't you encouraging draft authors to use a higher level language formalism which can both draw the diagram and develop the code?
So that's a good question. So there's a couple of things. I think what we're trying to do with the sort of diagram-based language, which, as I say, is just an example of a description technique, is we're trying to encourage people that aren't typically drawn to using formal and structured languages to see the benefits of using them. And we think that using something that's quite familiar, so these diagrams are in use already, using that familiar language is a good sort of first step towards that. Once authors see the benefits of using formal and structured languages, I think you're right. I think there's certainly better approaches. I think the other point I would make is that there are other people working on the sort of literate programming type approach that you're talking about and you talked about in the chat. And I think there are approaches to that integrate well with what we are building. So, but yeah, I think the important thing is that this is just a first step towards using these languages. We want to encourage it. Okay.
So unfortunately, the time for Q&A has run out. Mirja, did you have a really urgent question?
No, I don't. It's fine.
Okay, good. Thank you. So thank you, Stephen. A reminder that if you would like to continue the conversation, you can either use the chat of the Meet ecosystem, but there is also the Slack channel on the SIGCOMM community Slack. And of course, authors will always respond to emails. That brings me to our next speaker, Narayan G. Of the National Institute of Technology in Karnataka, who is a fourth-year undergraduate student, who is a mathematics systems and network enthusiast, and is going to talk to us about NEST, the network stack tester. Alessandro, can you start the video?
Hello everyone, I am Narayan G from the National Institute of Technology, Karnataka, India. I will be discussing about our work on developing NEST or Network Stack Tester. My co-authors are Shantanu S. Rai, Dhanashekar M, Leslie Moniz, and Mohit P. Tahiliani. Performing network experiments and studying network protocol behavior is a non-trivial process. The most commonly used approach to perform network experiments is to set up a physical testbed that closely represents the desired network. But it is expensive even for a relatively small network, and more importantly, it is not scalable. Linux network namespaces are a suitable alternative to physical testbeds because we can quickly set up a lightweight emulation testbed for the experimental evaluation. Network namespaces basically virtualize the network stack. By isolating the network stack and creating multiple namespaces, we can emulate a network. In doing so, we can basically build a complex topology or emulate any real-life network using a single system. This approach enhances the reproducibility aspect and minimizes the maintenance and cost overhead. However, manually setting up testbeds and obtaining results in the desired format using network namespaces can be quite cumbersome and error-prone. However, there are tools like Mininet that makes the task of building virtual topologies easier. It is a tool specifically for building topologies using network namespaces. Once the topology is built, well-known tools like Flint can be used to run network tests. Flint provides predefined experiments and intuitive means to collect statistics. It can be used to test a physical topology set up using multiple systems, or within a system to test a topology built using network namespaces. Initially, we attempted to build a wrapper around Flint and incorporate topology set up using network namespaces. But Flint is designed to run from a single node or controller in a network. Also, it uses SSH to control and get statistics from remote machines. Using SSH to communicate between namespaces is an additional overhead. Although many-to-many flows and collecting statistics can be achieved with some minor tweaks, it is a difficult process in Flint. Mininet, on the other hand, provides nice APIs for setting up topology and using network namespaces, but lacks support for advanced traffic control. Transperf is developed by Google specifically for testing transport protocol performance. It expects a pre-set-up topology with physical systems, that is in multi-server mode, but handles creation of network namespaces when run in single server mode. However, it offers very little flexibility in terms of testbed configuration. Netesto is similar to Flint but has fewer number of tests and provides less data on statistics. Teacup, on the other hand, concentrates on testbed configuration and data collection but requires a physical topology setup beforehand. Each of these tools were created for their own use cases. Combining most of the benefits of these tools is the main motivation to develop NEST. NEST is a Python package which simplifies the process of network experimentation by using Linux network namespaces. The highlight is that it is a tool that can create a topology, add flows, run the experiment, store the data of the experiment, and get plots. It tries to combine all the aspects needed for running experiments. The APIs, we believe, are intuitive, which will be shown in the upcoming slides. The experiments are easily reproducible. All one would need to do is run the same code to reproduce the results. The resources required to run an experiment is much lesser compared to setting up a physical testbed. Even the prerequisites that someone needs to create their own network experiments are much lesser. One does not need to know about the internal details of NEST, like network namespaces, IP route to commands, netperf, etc. but they will still be able to create their own experiments. Nest allows different experiments to be run parallelly on the same topology by creating multiple instances of the same topology. Additionally, Nest is an open source project, and any contributions from the community are welcome, and the link for our website is mentioned below. Here is a sample code that is written with the Nest package. It creates a peer-to-peer topology and runs an experiment on it. You can take some time to look at it. First, two nodes are created, namely N0 and N1. Then they are connected using the Connect API. Next, IP addresses are assigned to these interfaces. Later, the setAttributes API is used to set the properties of the link between N0 and N1. Next, an experiment called myTest is set up and a flow is added to it. The flow API takes in arguments for the source node, destination node, and the destination address to uniquely identify itself. Additionally, the start time, stop time, and the number of flows is specified in the arguments. Note just a single flow is added in this example, but Nest allows adding multiple flows between any two pairs of nodes. Finally, experiment.run is invoked to run the experiment. After the experiment is complete, statistics such as throughput, congestion window, round trip time, and others are provided to the user as timestamped JSON dumps and plots. Moving on to the internal architecture of Nest. APIs like node creation, connect, set address, and set attributes internally hit the topology module. This module is responsible for creating the topology by using virtual nodes and interfaces. The topology module in turn calls the engine, which uses iproute2 commands to build the topology. Engine module runs iproute2 and netperf commands. It provides a set of low-level APIs for the other modules. For example, the initial two commands in Nest creates two network namespaces. The topology map maintains a mapping between the user-given names in the program and the names of the namespaces created by the iproute2 commands. This makes sure that no two namespaces have the same name, and also allows multiple network topologies with entities having the same user-given names to coexist in the system. APIs like flow creation, experiment, runs are part of the experiment module. The experiment module provides APIs to generate traffic and extract the statistics from the nodes and interfaces. Experiment module relies on engine to provide APIs for generating traffic and obtaining the required network statistics. For example, flow addition in experiment leads to netperf being run in the background. While presenting the results to the user, topology map is used by the experiment to convert the Nest's internal given names back to the user given names. Nest currently has support for setting up advanced traffic control, different congestion control algorithms, and queuing disciplines. The user can also configure the TCP congestion control algorithm, initial congestion window, and other TCP parameters that can be found in proc, sys, net IPv4. This is very useful since Nest provides control over parameters that can be configured in a Linux system. It allows the user to set up link parameters such as bandwidth and delay and configure the queuing discipline at intermediate nodes. All this can be used to set up a topology to be tested. For experimentation, Nest uses netperf to generate network traffic and parses the statistics reported by it to plot goodput. It uses SS utility, which is a part of iproute2, to obtain socket statistics like the congestion window, round trip time, slow start threshold, per flow throughput, pacing rate, and delivery rate of TCP flows. Nest uses TC utility to configure the bandwidth and delay of the links, configure the queuing disciplines, buffer sizes and filters on root interfaces, and extract queue disk specific statistics like queue length and queue delay. Other tools can be integrated with Nest easily in the future because it has a modular structure. As previously shown in the architecture, the tool-specific commands need to be added to the engine module and the required high-level Python API to the topology or experiment module suitably. About the limitations of Nest. It emulates the network stack and does not set up a real network. Hence, it lacks the support of hardware NICs. The effect of hardware level optimizations which are done in modern NICs are not reflected in Nest. For example, in the modern NICs, certain tasks that are otherwise done in software level are offloaded to the NICs. Also, to prevent buffer bloat, the NICs limit the size of the queue by the number of bytes. These effects are not visible in Nest. Another limitation is that Nest currently uses the network stack provided by the Linux kernel. So it is not possible to emulate a test environment with different implementations of the network stack, such as those in BSD, Windows, or stacks that run atop user space packet processing libraries such as netmap and data plane development kit, or also known as DPDK. Nest has limited support for debugging the test environment, which includes checking link status using ping. Interfaces to external tools such as TCP dump and traceroute shall be added in a future release. To validate the results obtained from Nest, we ran two experiments. Let's take a look at the first experiment. This experiment was conducted to see how accurate are Nest results compared to that of a physical testbed. The same topology was set up in both. As the diagram shows, we had two endpoints, node 0 and node 1, and a router between them. The link between node 0 and the router has a latency of 5 milliseconds and a bandwidth of 1 gigabit per second. And the link between node 1 and the router has a latency of 10 milliseconds and a bandwidth of 100 megabit per second. There are 4 TCP upload flows from node 0 to node 1. Control delay or codel queue discipline is used at the router with a target queue delay of 5 milliseconds, an interval of 100 milliseconds, and a queue limit of 1000 packets. This experiment is also repeated using FIFO queue discipline. We can now see how the results of Nest compare to that on a physical testbed. We see the results from Nest on top and physical testbed below, with codel results on the left and FIFO on the right. We observe that the congestion window plots exhibit a very similar behavior. Next, we observe the throughput distribution for each flow. When codel is used, the throughput obtained for every flow is fair because codel has a better queue control and avoids bulk packet losses due to congestion. FIFO, on the other hand, has poor queue control and leads to bulk packet losses when congestion occurs. This results in an unfair allocation of the bottleneck bandwidth among 4 flows. Next, we see the link utilization and queue backlog. As expected, the bottleneck link is fully utilized with FIFO queue disk. Codel keeps the backlog under control while keeping the bottleneck bandwidth fully occupied, whereas while using FIFO, there is a high backlog due to passive queue management. Note that the y-axes are different for codel and FIFO. Moving on to the second experiment, we tested how well Nest performs on a fairly complex topology and hence build the topology shown in the figure. It comprises of 12 nodes and 5 routers, with all the links connecting the routers being bottleneck links. Every sender uses cubic TCP and the routers use FQ codel, which stands for flow queue codel, which is the default queue disk in Linux. Codel's configuration in FQ codel is the same as described in the previous experiment. In the figure, we see A brackets 3 on node 0 and node 6. This indicates that 3 TCP flows run from node 0 to node 6. The similar convention is followed for other flows. We compare Nest against a setup in which the topology is manually set up using network namespaces and traffic is generated using Flint. Now we can see the results obtained for the experiment. We present the congestion window, throughput and round trip time only for flows from A because they traverse via multiple congested routers. We can see the plots for Nest and Flint are very similar. Next, we present the link utilization for router 0, 1 and 3 to cover the links of different bandwidth. Again, we see that Nest and Flint lines almost overlap each other on the plots. In the experiment, we have collected TCP stats from all the nodes and network stats from all the routers, but haven't shown them here due to time and space constraints. To view all of them, please visit the website link provided in this slide. Also, we have provided the same link in the paper too. On a concluding note, I would like to mention that Nest is freely available on PyPI and can easily be obtained using pip utility. Additionally, Nest is an open source project. We'll try to actively maintain this tool, and any contributions from the community are welcome. Here is a link to our website. Now moving on to the Q&A session. Also, here is our email ID if you want to follow up with any other questions. Thank you.
Okay. Thank you, Narayan. I let you into the session. If you want, you can also share your video. I'm also letting in your co-authors. I saw some discussion about the paper on the chat. So if people have questions, please feel free to join the queue. And in the meantime, I'm going to switch and pop up the slides. I have a question from Mirja. Mirja, go ahead.
Yes. Let me put on my camera as well. You can see me. I saw in your paper that you do mention Mininet as something similar, but actually designed for a different purpose and more testing SDN-like networks and not protocol stacks. But I guess the step from Mininet to your tooling isn't actually that much. So did you compare that, or what's missing? What's the big difference?
We have somebody with very loud background noise. I don't know who it is.
Did you just accept all audio, maybe kick out the other people again?
Yeah, I've kicked out a few people. Sorry, folks.
Could you repeat the question? Sorry.
The question was like, how does it compare to Mininet? And wouldn't it be possible to, for example, also add something to Mininet to get the same features? Or what's the big difference?
Mininet actually lacks a few support for a few features of complex traffic control. So we've also included that in ours, and yeah, for testing we included Flint. So since it lacked advanced traffic control, we thought we would build it, we would add it from the Linux NetNS itself.
Okay, and so it wasn't an option to just kind of building add-ons for Mininet. Why did you decide to build something completely new?
We thought each and every tool was meant for its own purpose. So we thought maybe constructing a tool of our own could maybe be specifically for this purpose. So maybe that would be easier, and we would have total control of everything, and we would, yeah, so that would be the reason, I guess.
Okay, thank you.
Yeah, maybe I can add a bit, Mira. I'm Mohit. I'm also the co-author on the paper. So one of the work that we were doing at our team was primarily on the TCP and Q disciplines, and we have been closely following the efforts on L4S and SCE at TSPWG. And we wanted to kind of replicate the experiments that we saw in the Pete Heist repository, which were kind of being used for evaluating the performance of upcoming L4S standards and SCE standard. So one of the reasons we did not modify Mininet is because, like Narayan said, that it did not have very advanced features supported for traffic control, which was important for our experiments. And kind of tests which were used in the Pete Heist topology, which we were trying to reproduce, was using Flint. So we wanted something like Flint on top of Mininet, and we thought that stitching these two tools was very difficult for us. So instead, we thought we could just build our own tool, which will be much easier for us and simpler for us. And also, we wanted to make it as reproducible as possible for the other researchers.
Okay, thank you for the response. Because there's we have 2 minutes left and we have one more question.
Sure.
Can I cut you off? Okay. Chris, go ahead.
Yeah. So I saw you had a slide in there where you compared the difference between the physical network configured similarly to the virtual network. I was wondering if you could speak a little bit to the differences you found between physical and virtualized networks, because one of the questions that we always have, and one of the reasons that we might use physical networks is because we are concerned that the results that we have on the virtual setups won't reflect reality.
Yeah, sure. So one of the things which I think we discussed in the limitations is that if you use these network namespaces, we typically do not get the behavior that we would expect if we use algorithms like BQL. So when we use physical testbed, BQL is by default enabled over there. So we cannot capture those kind of details in the network namespaces. So there are minor differences with respect to that when we compare with the physical testbed. Yes.
Thank you.
Okay. It looks like that is the last question we have. Thank you. Thank you to the speakers as well for their presentations and answering the questions. I'm going to quickly pop up the previous slide I was showing. Let me go. There we go. So this is the end of session 2 of ANRW. We will be back at 10 minutes past 2 UTC. That is in 20 minutes from now. With session 3, this is the final session of today, which has 4 papers in it that are shown on the screen here. Thank you all for attending this session, and I hope to see you all back in 20 minutes time. And thank you also to our speakers. And that's it from me.